our next meetup. So that's another one meetup that we are hosting online. Hopefully we will be able to get back to offline format, but it will not happen in the nearest time. That's why also we decided to experiment with quite unusual time for our events. Usually, as you know, we would meet somewhere around 5 p.m. or 6 p.m. so that we can feel free from our work obligations. But you know, today many of us spend time at home even during the lunchtime, and let's see if this lunchtime format is somehow interesting for our group. Today we've got a pretty seasoned expert, an Apache Ignite expert, who agreed to join our group and present to us. So if to be more specific, Stan is our speaker. He is one of the few Java experts who initially contributed to the Java platform. And now he works with distributed systems such as Apache Ignite that are essentially powered by Java. So he is a seasoned expert in JVM internals, concurrency, memory management, and he gained that knowledge by working for Oracle for many years. And since 2017, Stan joined GridGain and Apache Ignite community, and right now he spends most of his time helping many architects and developers to build highly concurrent systems that are powered by Apache Ignite, by Java, etc. And also Stan leads a group of experts at GridGain who involved in design, maintenance, and operations of customer services and applications used by millions.
Thank you so much, Dennis. And hi everyone, my name is Stan, and today I want to talk to you about networking in distributed systems, talking mostly about Apache Ignite, by using it as an example to illustrate how a distributed system may implement its networking layer to support everything else that's running in a distributed systems cluster. So thank you all for joining today, and without further ado, let's start. So I want to start by talking a bit about what does network even do in a distributed system. So obviously network, well, some would say that network does everything in a distributed system because it's distributed.
Sorry for interrupting you. Do you show any other slides rather than the raffle one? Yep.
Oh, I think I'm okay. Sorry.
Yep.
Okay, now we see it. Okay. Yeah. So what does the network do? First of all, obviously, our distributed systems are designed for data processing, and first of all, we need to transfer data over the network. But this might seem like the only thing that the network does, like data transferring, but actually a networking component and the basic networking protocols running in a distributed system do a few more things. So first of all, in addition to actual data valuable to the business, you might also have some additional system cluster events. And these events would be the ones controlling the state and controlling the operation of your system. So these are the two main kinds of signals, the two main kinds of messages which would be floating across your system. And also a networking component is responsible for just getting your cluster together, for getting your nodes to find each other and to be able for them to be able to connect. And also, if one of the nodes fails, you also need to detect that. And normally this is also done on a level of the basic networking protocols. So next, let's talk a bit about our hero today, about Apache Ignite, which is going to be our reference system, the one we will take as an example. For those of you who are completely unfamiliar with Apache Ignite, it's an in-memory data processing and computing platform. It is a distributed platform which provides a lot of different features for distributed data processing, such as key value grid, SQL grid, distributed computing services, etc., etc. And there is also GridGain, the company I work for, which provides additional enterprise-grade features on top of Apache Ignite. But what we are going to talk about today is not all that. What we are going to talk about today is this distributed in-memory tier on this slide, just the basic networking components which allow all of this feature to function. Next, before actually getting to the networking, I want to give a few definitions which I will be using, and I've started using it already quite a lot, which we need to get on the same page with. And a warning, these definitions are very simplified, but I'm just putting them very plainly, which will be quite enough for our talk today. So first, a node. A node, you can think of it as any machine connected to a distributed system, a part of our system. The cluster is the system itself, all nodes together, the collection of all of our nodes connected. Server or server node is a kind of node that stores data in Apache Ignite. A client or a client node is a kind of node that does not store data. Typically, this is a node which represents an application. An application would include a client node in itself to connect to the cluster of Apache Ignite and to be able to communicate with it. Finally, discovery and communication. While these are very widely used terms in information technology today, when I will be saying discovery and communication, I will be referring specifically to Ignite's components with these names. These are the two networking components which we are going to talk about. Then let's start talking about the distributed system, the networking functions in a distributed system. And let's start with the first one, the main one, and the simplest one, the data transfer. So what we can say about transferring data in a distributed system, in a distributed cluster. First of all, this is what defines how well our system performs. If we transfer data fast and reliable, then the system is good. If the data transfer is slow, the system will not perform, obviously. Second, almost all of the traffic, if you consider a highly loaded system, almost all of the traffic would be the data transfer, transferring actual user data, from the applications, not some metadata, not some system signals. So it all leads us to an observation that the key for transferring data is transferring it fast. And by fast, we need to consider both latency of the data transfer and throughput. In Apache Ignite, data transfer is handled by a component which is called communication. So communication is a networking component and protocol of Apache Ignite, which handles high-speed data transferring. Almost all operations in the cluster use communication. Data modifications, queries, computing services, everything that is initiated by an application would most likely be using communication, first of all. To ensure high performance communication in Apache Ignite is implemented using Java Nio. For those of you who are not familiar, Java Nio is standard framework from the standard Java library, which allows to implement optimized multi-threaded I/O components, in particular network input-output. Since we want minimum latency, we want peer-to-peer connections. Why? Is because we want to transfer data in a single hop, and this minimize our latency. But this also brings a problem. And the problem is that if we, in a large cluster, if we just create peer-to-peer connections between every two nodes that we have, then we will have just too many connections and we need to budget them. They are quite a precious resource. And let's see how this is done and how a communication looks like in terms of the network topology. So communication. In this slide, in this scheme, you can see a cluster of 6 nodes. 4 of them are servers, 2 are clients, so 4 of them have the data, store the data, and 2 of them just access the data on behalf of some applications. First of all, logically, all nodes are connected in communication, and any node can connect to any other node. All nodes are equal. Any node can initiate any connection to any other. But if we just leave it like that, then as I've said, we would have way too many connections created all the time, and this would be a waste. And that's why connections are budgeted. Connections are created ad hoc, which means that if an application is idle, like the application on the right on this slide, it just won't have any connections open for communication protocol with any other nodes. In terms of communication, it is just disconnected from the cluster while it's idle. All the servers are typically connected to each other. Active applications would normally need to talk to all of the servers because different servers store different pieces of the data. So application needs to connect to each of them in order to work with all of the data stored in the cluster. So this is quite simple looking, but very complex in the implementation component, which handles transferring data in Apache Ignite, the communication. It is a component which is uses Java Nio to increase performance. It uses peer-to-peer communication to reduce latency, and it budgets the connection and creates ad hoc topologies in order to not exhaust the connection pool in the system. And this is our first function. This might be the simplest one, and this is how it is implemented. Again, it is much more complicated on the implementation level, but we wouldn't possibly have enough time to cover it all today. So we'll just leave it at that. The next one, it's cluster events delivery. And what can we say about it? So delivering cluster events, what does it mean? It means that if the system state has changed, if a state of, say, a single node has changed, so such that all other nodes need to know about that, we need to provide some protocol to be able to do that. And looking at more high-level distributed protocols, you can see that an ability to notify the entire cluster about the state of the system is the base for a lot of protocols which distributed systems use. Such protocol does not need to have high throughput. As I've said before, almost all of the traffic in the cluster would be handled by the data transfer. In our case, in case of Apache Ignite, it's communication component. So here we don't need to worry about transferring a lot of data. We just need to do it reliably and efficiently. And one last but very important thing, distributed protocols might not just need global events delivery, they also might need global events ordering. And this is because in some cases, you just have to know which events happened in which order. And this order needs to be viewed the same on all nodes in the cluster. And given that the system is distributed and parallel and asynchronous a lot of the time, the notion of happens before becomes quite tricky to capture. Let me illustrate it with an example. So say we have a couple of nodes in our cluster which simultaneously try to execute the same operation, a create table operation. And this create table operation has slightly different parameters to that, which are incompatible. So normally, if you just execute these two create table statements one after another, the first would succeed and the second would fail. So in this case, when these operations happen in parallel on two nodes, we need some way to know which one is to succeed and which one is to fail. And this might be quite a simple example, but I hope that this can illustrate the benefits of knowing, of having the global order of events. So how does Apache Ignite implement this? And how does Apache Ignite transfer deliver cluster-wide messages? For that, Ignite has a second networking component, which is called Discovery. So Discovery does a few things. Actually, it handles all three other functions which we have not covered yet, the three other functions of networking. It delivers ordered cluster-wide events across the cluster. It allows node to join the cluster and to find each other, and it also provides failure detection. So this one single protocol does all these three things, and let's look how exactly it does that. So first, let's talk a bit about how discovery topology looks like. So how the nodes are connected in the view of this discovery protocol. So in this protocol, we don't have peer-to-peer connections anymore. In this protocol, the core is the one-way ring which connects all of the servers. Why ring? Ring makes it quite easier to impose this global events ordering, because with when we have a ring, and when it is processed in a single thread, we only have one channel which all the events can use to be sent across the cluster. And this is how all the events get linearized. Also, we have clients, and here clients are not the same as servers. Unlike in communication, which for which all nodes are equals, in discovery, nodes are not equals. We have clients, and clients are not parts of the ring. Clients are connected to servers from outside of the ring, and this is done to ensure that slow clients will not cause slowness of the core of the cluster, of the servers. Applications quite often might be slower and less powerful machines than the servers which actually store the data. And that's why we normally want to protect the core of our cluster, the servers, from clients possibly slowing things down. And that's why clients are outside. Finally, servers are not all equals as well. One of the servers, this oldest server in the topology, the oldest server in the cluster, is called coordinator. And coordinator is the server which is responsible for all of the ordering of events. And this is like the main point of processing in the discovery protocol. And we'll see in just in a bit how exactly does it work. And as I've said, the processing here is single-threaded, and single-threaded processing also helps us to impose these ordering devices. So how are messages delivered in this discovery topology, in this ring with clients outside of it? Let's say node number 1 in this picture wants to send a message. We don't care about what is the message at this time. We just say that this is a message which all nodes need to receive, and the node will be sending it via the discovery protocol. So the message starts on node 1 as an unverified message. And unverified means that it has not been assigned order just yet. The unverified message travels across the ring towards the coordinator. None of the nodes process the message. They just pass it along. And then it goes to 3, then it goes to coordinator, and the coordinator verifies the message. Verified basically means that the message has been read by the coordinator. Now, after the message has been verified, the message, we actually know the order of the message, of this message. Basically, we define the order as whoever got to coordinator first is the first, is the event that has reached coordinator the first is the earlier event in a set of events. So next, coordinator, after it has processed the message itself, it sends the verified message across the ring. Then all servers can now process the message and pass the message not just to other servers, but also to the clients. And this is how the message reaches full circle, makes a full circle, actually 2 circles, and reaches all of the nodes, including the clients. And this is it. This is the entire message delivery protocol in the discovery subsystem. Key points about the protocol. First, we noticed that each message makes 2 circles around the ring. The first circle is just to make it to the coordinator, and the second circle is to actually be delivered and processed by all of the nodes in the cluster. We also said that we defined order by using the coordinator verification. And event A is considered to be earlier than event B if it has been verified on coordinator earlier than event B. So now, to answer our earlier question, we can say that if given 2 events happened on 2 nodes in parallel, which one will be considered to happen the first and succeed, and which one will be considered to happen the second and fail? Well, the one that reached coordinator the first will succeed, and the one that reaches coordinator the second will fail. And it basically means that whoever is closer in the ring to the coordinator, node 1 or node 2, that node will win. And this is it. This is how the message delivery happens in Discovery. This is how it is implemented in Apache Ignite, the cluster-wide, global, ordered message delivery. The next function of networking that we are going to talk about, it's how the nodes are connecting to a running cluster. So what does a new node needs to do to be connected to a cluster and to start exchange data with the cluster? First, it needs to find the cluster. And by find the cluster, I mean it needs to understand which IPs it's going to connect to. They can be provided right in the configuration. They can be found in some other way. We will see how it can be done. Then it needs to, after it has found a node it could connect to, it needs to send a request, and the nodes need to handshake. So the new node needs to be allowed to join the cluster. And finally, the new node needs to exchange information with the cluster, exchange some meta information. It needs to provide information about itself to all of the nodes already connected in our system. And it also needs to load the information about the nodes already connected. In Apache Ignite, connecting to a cluster is handled by Discovery subsystem. And in particular, finding a cluster, finding the IPs to connect to, is handled by a small but very important component, which is a part of Discovery, which is called IP Finder. And this is the component that provides us with a list of IPs. How it does that is by one of its many implementations. The one that is most widely used is the static IP Finder, which basically means that each node on the just in the configuration has a list of predefined hard-coded IPs which it will be trying to connect to, which makes a lot of sense in most systems, especially when running on bare metal on premises. There is also a multicast-based approach when we just ask the entire network around us whether there are any running Apache Ignite nodes. Maybe there are, maybe they will just respond and we will just find each other like that. There are a few approaches which use some form of a shared file. So it is a shared list instead of being hard-coded in a configuration of each and every node. We just have a shared list of all IPs which can be updated dynamically by all of the nodes when they join the cluster, when they leave the cluster. And finally, probably the most advanced way of doing that is by using a more complex tools for service discovery, which are quite big for Kubernetes environments and for cloud environments such as AWS and Google Compute and Azure and all the others. So this is what everything what IP Finder does. It provides you with an IP by using some resource, either a static list of IPs or some form of external resource or external search. Next, let's talk about how how cluster join actually happens. So we already know that it's going to happen by the help of discovery subsystem, and it's going to happen with the help of IP finder. Let's consider this. A cluster for nodes, for server nodes, and we want to join a new node, say a client. First, a new node starts. Then a new node, after starting, it asks its own component, its own local IP finder component, to provide it with an IP to try to connect to. And IP finder provides an IP with whatever implementation we have chosen. Then it's quite simple. We ask the node on the provided IP whether we can join. The node responds, hopefully that we can join the cluster at this time, and the discovery link is now established. So now it looks like the topology is complete. It looks the same as when we talked about discovery before, right? But not quite. The issue is that the node has just joined, and it knows a bit about the node number 1, because this is the node we are connected to, but we know nothing about nodes 0, 2, and 3. And these nodes also don't know anything about us, about the newly joined node. So what we will use discovery message delivery to send a discovery message, not joined. And this message will have all the information the cluster needs about us, about the new node, which every node will save, and most importantly, this message will contain our own IP address and the addresses which other nodes will be using to connect to us via communication to actually do something useful and to actually transfer data. And yeah, just by using the algorithm, the protocol which we have discussed before, we will deliver the not joined message to all of the nodes in the cluster. And yeah, this is it. This is the entire join process. Key points about this process are: first, a new node needs to find a running server and start by establishing a discovery link with that server so that it is now connected via discovery with the entire cluster. Then discovery is used to exchange information between that node and the cluster so that all nodes have enough information about each other in order to establish communication links. After that, discovery link is already operational. Communication is ready to be operational because all nodes have addresses of each other, and the cluster join is complete. So this is our third networking function, and here is our last one, and last but not least is the failure detection. And failure detection is a very important function of any distributed system. What it does, it defines high availability properties of our cluster. If our failure detection is insufficient, if it is slow, if it is unreliable, if it's just simply not there, then just failure of a single node being undiscovered by the cluster might cause entire clusters instability, cluster freezes, basically whole system outage. But before talking about how we are going to do failure detection, we also need to think about what failure means in terms of a distributed system. First of all, idle must not be confused with failed. A node can be idle, but it needs to be in a standby. We can say that if a node does not exchange messages with us for a long time, if it does not perform any useful operations, we just can't kick it out of the cluster. No, we can't, obviously. Normally, a failure in a node failure in a distributed system is attributed to whether a node is reachable over the network. And it means that what we will be doing, we will be trying to find a way to constantly check whether a node is reachable. And remember, we now have two ways of being reachable because we have two network protocols, discovery and communication. And finally, failure detection must not be ad hoc. It needs to happen continuously, because if a node fails, we need to find out about it as fast as we can. We can't delay it until we actually need to find the node, because it will mean latency spikes, freezes, and unhappy users. So in Apache Ignite, the component that handles node failure detection is also the discovery protocol. Basically, in Apache Ignite, we say that discovery connectivity is what defines node failure. Unreachable via discovery means you're a failed node. If we have not heard from you via discovery for some time, you're a failed node. Note that not hearing via communication does not mean that node has failed, because it might just be idle. But discovery needs to always be operational. And to ensure that, the nodes constantly send special messages to each other via discovery protocol, which are called heartbeats, or in modern Ignite versions, they are called metrics updates, but semantically, this is what other systems call heartbeats. And by constantly sending heartbeats, by constantly, I mean every few seconds, we can make sure that all nodes always receive discovery messages from one another, and that's how we ensure that we can always tell whether a node is failed or not. And how the failure detection actually works. Here, I want to look at a couple of examples. So the first one, say we have node number 3, which is faulty, and this is a node we would like to remove from the cluster. In the first example, say the node number 2 fails to send the message to number 3 via discovery. It may mean that node number 3 is completely unavailable. The machine has just crashed, or process has just crashed, and the socket is not listening. Maybe we can write to the socket, but we are not getting acknowledgement from node number 3. It may mean that the node number 3 is in a GC pose, in a JVM pose, something like that. So the node might be frozen or completely dead. In this case, node number 2 eventually will just realize that it cannot write to node number 3. And what it will do, it will just bypass node number 3, connect directly to 0, and ask coordinator to kick node number 3 out. There will be some exchange in discovery messages through the same discovery protocol which we have discussed before, and these are some lower level details which I would not dive into, but all in all, the cluster, the ring will just shrink, and node number 2 will now be connected to 0 directly. In the other case, maybe 2 can write to 3 successfully, but 3 just never writes to 0. it can't do it for some reason, maybe 3 is hanging, maybe there is some issue with the process. So node number 0 does not receive messages from number 3 for quite some time. The result is actually the same. After some time, eventually node number 0 will realize that node number 3 is not sending anything to it for a certain timeout, and it will also initiate the kick out procedure and distribute the new cluster state across the cluster with a discovery message, and it will tell node number 2 that it now needs to connect to node number 0 directly. And yeah, these are the 2 basic use cases, the 2 basic scenarios for failure detection. And yeah, this is how it works. And this concludes our overview of network functions. And I want to finish it by giving a short comparison between discovery and communication subsystems in Ignite. Again, communication is the one that is responsible for just sending data as fast as it can, and discovery is responsible for reliable, ordered cluster-wide messages delivery. And since the 2 subsystems are so different in the goals that they have, for one the key is speed, for the other the key is reliability and ability to provide ordering. By having that, we can see how these 2 subsystems use different approaches for establishing nodes connections, but and quite efficiently can fulfill their functions, implement their functions, and complement each other to serve as a base of all of the nice features that our distributed system can provide to us. And I also have a couple of more advanced topics, but I see that we are a bit out of time, so don't worry. You'll get the slides, and I'm sure that these advanced topics might be quite understandable from the slides too. So I would like to first go to the questions, and maybe after that, if we have time, we can return to the advanced topics. So yeah, and before the questions, I would like to add, if you want to have some hands-on experience with distributed systems, if you want to participate in development, please join our Apache Ignite community. The links are on this slide, and we will be very, very happy to have you on board. So thank you, and now I'm ready to take some questions if we still have some time for that.
Yeah, thanks, Stan. Thanks, Stan, for kind of walking through us these internals of Apache Ignite. Generally speaking, kind of my summary, and can correct me if I'm wrong, many distributed systems like take Apache Ignite, Cassandra, or Kafka, all of them in general have something similar. And then the only difference is how those protocols are implemented. But in many systems, like let it be any other system, you still would need to have some peer-to-peer communication layer. And also you would need to have some networking component that can process your events in like kind of with some specific order in mind.
Well, yeah. Well, basically any system would start by, again, implementing some way of doing peer-to-peer communication. And then on top of that, you need to add a protocol of sending a cluster-wide event. And I think it might be like intuition might tell you that just sending a broadcast message from every single node to every other node is not the best approach there. So we are trying to make this cluster-wide delivery more efficient, and we need a different protocol for that. And on top of that, we also want to define some ordering. So yeah.
Wonderful, wonderful. So let's do this. While we are taking the other questions, why don't we show the raffle slide? Because those of you guys who joined us a bit later, before the presentation started, today we are giving away these 3 wonderful books. So you can find a link to the raffle survey in the chat window. So you can find the chat window down the interface of Zoom, or it might be already open to your right. So do this, sign up, and while we are waiting for that, let's take the questions. Actually, Stan, I kind of posted a couple of questions from my end. I do know like some of the internals, but still I wanted to clarify those points from you. Let me read them out loud. So the first one, whenever you were presenting the communication layer, you mentioned at the very end of one slide that we use a single thread to process your, like, no, that was about the discovery. Yeah, we are using this, yeah, a single thread. Does it mean that was it related to the situation when every given server node has a single Java thread running, and that thread actually receives and generates and processes all the discovery events? What was that?
Yeah, in fact, there are when I say single threaded, I'm hiding the complexity a bit, because in fact there are a few threads, but they work as a as a single pipeline. So there is a thread which just reads the messages which come from the previous node in the ring, and puts the messages into some queue. Then there is a thread which would be processing the messages. Then there is a thread which would be sending out the messages. But the main thing here is that no message can go around the message. So the messages can't reorder. And if I send to discovery message 1, then message 2, at no place in discovery they can just reorder, and 2 will never be before 1. And to ensure that, you kind of have to have this single pipeline, single pipeline approach.
All right, understood. And also the other question, it's also related to Apache Ignite. But before I ask that question, guys, those who are on the line, just put like paste +1 in the chat window. You can use this reaction button if you're familiar with Ignite. And if you're not familiar with Ignite, like do this. You can find the icons. We just want to understand how many of you you're aware of that technology. So that question is, when you were talking about those system discovery events and messages, I did not hear any specific examples. Could you give us some basic understanding of that? What are those events? How exactly Ignite? What are the operations of Ignite that are handled through the discovery?
Well, these are, you can think of all of the operations which are, on one hand, they are global and every node needs to participate. And on the other hand, they are not necessarily absolutely rare, but they don't happen a lot, and they probably don't happen in the course of just every transaction, you know. So the operations like that would be everything related to nodes joining or leaving the cluster, because this is global cluster or cluster state change. The other example would be creating new caches. And cache, for those who are not familiar, cache is basically a bucket for storing data in Apache Ignite. So whenever we create a new bucket to store data in Ignite, it will also be done over discovery. And whenever we destroy a cache, it also require a discovery message. Also, there are these heartbeats, as I've said, but this utility message, which is used to just constantly have something flowing around the discovery topology in order to ensure that every node is responsive. And there are quite a few messages, other messages actually, but all of the others would, I would think they would relate to different Ignite features, so they might be a bit harder to cover.
All right, understood. So the summary, basically, whenever a cluster topology changes, like a new node joins the cluster or some other node leaves the cluster, then some SQL-like operations when you're creating table, right, or you're creating cache.
Yeah, like DDL, yeah.
Like create index command, etc. Alter table, yeah. In those cases, we definitely need, some guarantees related to the ordering of those events.